Hello and welcome back. In 11.7, we get to work with the counting principle and permutations. So we've already seen the counting principle. We just sort of expand on it. We saw before that if we have an experiment, one can end in m ways, and experiment 2 can end in n ways. Then there are m times n ways that the combined experiment can come to an end. We can expand that beyond just 2 events or 2 small experiments. So one common place we see this is license plates. So let's look at how many ways can a plate have one letter followed by, I pick 5 digits. So if we're allowing all 26 letters of the alphabet, we have 26 ways for that first part of the experiment to come to an end. So the first character on the plate is our first quote-unquote experiment. Then we have 5 digits. Well, we have 10 digits, 10 digits again, 10 digits again, 10 again, and 10 again. So 2,600,000 possible plates. Again, this is assuming the letter O is allowed. If letter O is not allowed, then we have 25 options for the letter, 10 for each of the digits. So 2,500,000 plates possible. And then we look at some other restrictions that we can put on it. What if they didn't allow us to repeat numbers? Well, we have 26 for the first. 10 digits to choose for our first digit in the plate. But once I've used that one, if they're saying no repetition, I've burned that one. If I use a 7, 7's out of the game. Now I have 9 other single-digit characters to choose from. Once I've picked one of those, now I have 2 in my hand, 8 more to choose from. Once I've selected those 3, I have 7 left to choose from, and so on. So this would allow us 786,240 plates. So another place that we could see this, there's a fun little problem, the school bus problem. So let's say there are 7 kids at one bus stop. And let's say the kids have been arguing amongst themselves, and about who wants to be first in line, who wants to be last, who wants to be in the middle. And so the parents get together and decide, well, we'll just keep using different orders until we run out of ways for them to line up for the bus. So how far into the school year do you think they'll make it before they run out of options? Well, now let's take a look. So let's say our kids are A, B, C, D, E, F, and G. Well, if we're lining them up when we haven't started the line yet, we told the kids, go stand over there, we'll call you over one at a time. I've got 7 kids to choose from. Once I've done that, put that kid at the front of the line. Now I have 6 more kids to choose from. Counting principle says we'll multiply these. Then 5 kids to choose from, and so on. And I'm going to keep going until I put my last kid into the line. So if you dial that into your calculator, you'll see they're going to very comfortably make it through many school years. There are 5,040 ways to line up the 7 kids. And they can occasionally pardon me, put restrictions on a problem like this. So let's say they want to put kid A must be in, we'll call it slot 4, the middle. Well, then I have only one person for this 4th position in line. Kid A is already sitting there. That means that now I have 6 kids to pick from when I start, then 5, then 4, then 3, then 2, and then whoever's left over. So this would put us at now 720 ways. So this is only, now just a couple of school years. Or maybe we had 2 restrictions. Kid A must be in slot 4. Kid G must be first. See if you can find out how many ways this will happen. Go ahead and pause it if you need to. Welcome back. So our first slot is occupied by kid G, and there's only one kid G. Second slot, I can't pick kid A for that. Kid A had to be in the 4th slot. So now I'm down to 5 kids to choose from, then 4 kids, 3 kids, 2 kids, and 1 kid. So there were 120 ways. So this time, if 2 of them have to be in a certain spot, now they will have repetition during the school year. We're down to 120 ways that this can happen. Now I want to talk about the idea of permutations. So first off, what is a permutation? It's an ordered arrangement of a given set. That's why we covered the license plates in the permutation section. The order does matter. If your license plate is 1, 2, 3, and someone else drives past a speed camera, a speed trap camera, and their license plate is 231, you certainly don't want their ticket. The order of those digits does matter. So an ordered arrangement. So for example, on let's look at a set of 3 objects. So some possible orders, some permutations would be in that exact sequence. ABC is one permutation. ACB would be another. Those are the only ones that will start with A. This might take you back to our graph theory work. You might see something similar that we did back then. BAC, BCA, those are all the ones that'll start with B. CAB, CBA. And those are all of them. There are 6 possible permutations. And 3 objects. And if you'll recall, 3 factorial is equal to 3 times 2 times 1. There's our 6. And in general, there will be n factorial permutations on n objects. So those 7 school bus kids, 7 factorial is 5,040. So if I had, say, 5 objects, without having to go through this with A, B, C, D, and E and rearranging the letters, I know that I have 5 factorial, 5 by 4 by 3 by 2 by 1. 120 permutations exist. The next idea, though, that comes up with this is, what if I have that bigger collection of objects, but I don't want to use them all? So what if we don't want to use all of those objects? We just want to use, let's say, k of them. So some new notation here. So to select k objects from a set of n, there are, and this would be written as n, p, k, n factorial, and we would divide by n minus k in parentheses factorial. So n factorial over n minus k factorial permutations exist on those objects. So let's say we have a class of 24 students. We're going to select 4 for 4 different jobs. In other words, the order you're picked matters. Well, how many ways could we pick 4 students from a class of 24 where the order is important? Well, that would be 24 P4. So 24 factorial over 24 minus 4 in parentheses factorial. So 24 factorial over 20 factorial. Now, I could expand each of these all the way down to 1, and I'll kind of show you the start of it, and I'll let you make an observation about why I wouldn't expand these all the way down every single time. So hopefully you notice that since this is all multiplication at the top and all multiplication at the bottom, 20 over 20 is 1, 19 over 19 is 1, 18 over 18 is 1, and all of these are going to cancel out. So instead of writing it the long way like this, what we do is we expand the 24 factorial until we get to 20, and then we call it 20 factorial. And we know that 20 factorial in both cases means 20 times 19 times 18. So we would typically skip this middle part here and proceed right to here. Cancel the 20 factorials. So 24 times 23 times 22 times 21. And then we just plug and chug in the calculator on that. And we're at 255,024 ways. And again, that's if the order matters. So I'm going to have you all try sort of a smaller one. So let's say there are 8 candidates. And we want to know how many ways and 1 president and 1 vice president be selected. So go ahead and pause that and see what you come up with. See if you can figure out how many ways. Okay, welcome back. So this would be order is important. A president and a vice president, definitely not the same job. So of the 8 candidates, we're selecting 2 of them. So this is 8p2. So 8 factorial over 8 minus 2 in parentheses factorial, which turns into 8 factorial over 6 factorial. So I expand the 8 factorial until I hit whatever number's at the bottom there. And then I just slap the factorial on both. So we have 56 ways to select president and a VP. So all of these examples have been using people, but sometimes we have identical man-made objects. How do we work with that? For identical objects, we have n factorial over k1 factorial, k2 factorial, 2kr factorial. Where there are n objects total, k sub 1 identical, k sub 2 identical, etc. So let's say that we have 3 Mth115 books, 5 Mth115 books, and 2 Mth165 books. So those 3 Mth115 books for our purposes are going to be identical. Same thing with the 2 Mth165 books and the 5 Mth195 books. I can't tell one Mth195 book from another, so we're assuming they're not written in or anything. They're just identical. So I want to know how many ways can the books be placed on a shelf. Well, all together I have 10 books. So 10 factorial upstairs, 3 identical objects, 5 identical objects, and 2 identical objects. So our biggest factorial downstairs is 5, so I'll expand the 10 factorial until I hit a 5. It's 10 times 9 times 8 times 7 times 6 times 5 factorial. Downstairs, I'll keep that 5 factorial the way it is. 3 factorial, 3 times 2 times 1. 2 factorial, 2 times 1. And then we do some simplifying. So 5 factorial over itself. 3 times 2 times 1 is 6, and I have a 6 upstairs. And let's see, half of 8 is 4. So then we have 90 times 28, 2,520. $2,520 ways that we can order those books on the shelf. So maybe one order has all 3 of the 115 books, then all 5 of the 95s, then both of the 165s. Another order might have one of each at the front, and then 2 115s, 4 95s, and 1 165. All told, 2,520 different arrangements that we can make. Where, again, we cannot distinguish the 115 books from one another or the 95 books from one another. So some problems to try out. This was in section 11.7. I would recommend 9 to 15.9 on the odds. If you have any questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.